last class we started about the power factor problems associated with phase controlled converters. Then we studied what is the problem with a single phase fully controlled converter, and we found that for a single phase fully controlled converter, that is a single phase fully controlled converter, this is the, we have 4 thyristors. 4 thyristors will be controlled, and commutation is natural commutation, that is when the incoming phase, that is now the phase which is turned on or the thyristor which is turned on will switch off the previously conducting thyristor at the bottom, or also at the same at the, when the bottom thyristor is turned on, the previously conducting thyristor at the bottom will be turned on. Now, so with respect to the firing angle, suppose this is our mains voltage. For continuity again I will be talking about the, this one, and assuming current is highly output current is highly DC, we are assuming the ripple is negligible. When the top when the top device T1, T1 and T4 are turned on, current will be going like this. When the T2 and T3 are turned on, the input current will be like this, but output current will be the rectified version of this current at the load side. So, this is the current waveform at the input side, that is this side, input side. The fundamental component of this current will be approximately something like this. The phase relation with respect to the total current and the fundamental current is something like this. So, if you see, and also we know that the input power, that is a fundamental RMS power, that is the one which will be of any useful, it will be of any useful work transferring from the source side to the load side. So, the fundamental power P in input power is equal to Vrms, that is the input RMS side, voltage RMS, then the current RMS of the fundamental I1R into the phase difference, displacement angle between the two, the voltage and the current waveform. Here, because of the firing angle is initiated at alpha. So, current will start moving, start flowing through T1 and T2 at this point. At this point, T1 and T4 will be conducting. So, the fundamental current is displaced by alpha. So, power will be cos alpha. So, as the firing angle increases, the cos alpha will decrease, and there is a decrease in the power factor. What is the and also we told what is the problem with the power factor? We told the power factor for the same power as the firing angle increases, input will draw large current, okay, large current, so that the power is constant. So, it can decrease the efficiency of the system, or on this higher current it can create losses in the system. So, we want ideal case to draw the maximum power for a particular condition or particular output voltage from the input is the current should be the phase angle or the displacement angle between the voltage and the fundamental current should be 0. So, that the power factor cos alpha should be unity, but in the phase controlled converter what we found it is cos alpha. Now, then we went for the semi controlled converter. The semi controlled converters are used when we want only the when we don't want the negative voltage, negative DC voltage, controlled voltages at the output. We only want the output voltage vary from 0 to positive. Then we will be using only the semi controlled converter. That means 2 thyristors are controlled. What is the advantage of that one? We can then the gate drives, we can have a saving on the gate drive circuit, and cost can be reduced. So, for the semi controlled converter, if you see here, it will be like this. We have taken in the last class, the semi controlled single phase full wave semi controlled converter will be like this. This is the diode. Okay. We have 2 diodes, bottom portion we are using only diode D2, this is D1, and top you will have the thyristors to control the output voltage. Okay. So, this is our load. So, we can represent as a DC motor. So, here this is the input I1 current. So, here how the the fundamental current with respect to the input voltage will be. So, here it will be, if you draw the waveform, this is our mains, okay. Then the current waveform. See, because of the diode, as I told before, whenever the diode forward biased, it will not wait for the any gate drive circuit. Whenever it is forward biased, immediately it will conduct, but thyristors will switch off when the next thyristor is turned on. So, when T1 is turned on, at the positive side T1 is turned on, when this point, that is this point, when this point becomes when this point becomes negative, this diode will immediately conduct, and unless the this thyristor is turned on, that is this T2 is turned on, T1 will not switch off. So, during the portion when this point goes negative, there is a short circuit through this one, and the output voltage will be 0. So, the current waveform, if you see here, input current wave during the freewheeling period, input is not giving any current to the output. So, that point it will be 0, then here this way it will come. Then the input current is like this, input current waveform is like this. This we have talked about in the last class. Okay. Here the fundamental, if you see the fundamental, let us draw with a the current fundamental current waveform will be approximately like this. So, even though firing angle is alpha, this is the alpha, the displacement angle is, that is from 0 side, 2 zeros, voltage 0 crossing, current 0 crossing, it is, this is phi is equal to alpha by 2. So, here the power factor, there is an improvement in the power factor. Okay. Now, ideally speaking, what we want, unity power factor. So, is it possible for us to get a unity power factor? Then what is required here? So, let us take a semi-controlled converter. So the same semi-controlled converter, let us take a condition like this. This is our mains waveform, voltage waveform. Now, if we can have a current waveform like this, that is the conducting period through the input side is centered at the mains phase voltage. Okay. This is the current waveform. Then what is the advantage here? Here the fundamental, even though we are getting pulsed current through the mains, the fundamental current will be always, the displacement between the fundamental current and the voltage will be always 0, and the power factor will be maximum, that is cos 0 is equal to 1. A condition like this you will get it. So, this is the best way of drawing power. How is it possible with a semi-controlled converter? Let us see. Again we will draw the power circuit. This is semi converter. So, bottom device are the diodes. Okay. Our input. This is the current we are talking about. How to get a current waveform like this. This is our T1, T2, D1, D2. How to get a condition like this? So, if you see this figure, the firing angle starts here. Alpha is equal to 0 here. This is the firing angle alpha, some firing angle alpha 1 starting from here. At this point, the current T1 and D1 will be conducting. This point T1 and D1 will be conducting. T1 and D1 will be conducting. Now, suddenly the input current stops here at this point. The current is stopped means the power circuit, that is the thyristors and diodes are not allowing any current flow from the input side to the output side. So, what we should do? In this case, at this point, we should switch off T1 by somehow. T1 is off. We have to switch off T1. That means we require a force commutator, some external circuits. Using some external circuit, we should force commutate this thyristor. But there is another problem. Previously, this current was, input current was flowing through the through this way. It was flowing, and it was returning back to the mains like this. Now, thyristor T1 is turned off. This current is there. Suddenly, you cannot change the load current. So, we should provide some other path for this load current to flow, and T2 is not turned on. Now, if you see here, the T1 turning off is not through T2 turn on. T2 is not yet turned on, and we have turned off T1 through some external circuit. We will study one circuit, one interesting circuit later. But thyristor will switch off, but current cannot die down immediately, load current. What will happen? If you switch off like that, there is no alternate path for the device to follow. di by dt suddenly will increase, and it will force the current to flow through T1. T1 will not be turned off. So, to make sure that T1 is turned off, what we have to do? We have to put another path, that is the freewheeling path here. We have to give diode DF. So, during this input 0 current periods, that is these periods, DF will be conducting. Okay? Then again at this point, we will be turning on, T2 is turned on, T2 is on. The moment T2 is turned on and the mains is negative, so D1 will be immediately turned on, because this point is negative now. So, D1 is forward biased and D1 will be immediately turned on. Now, the current will flow through this way. The moment T1 is turned on, this point will come across this one, D1 is turned on, this point will come here, this diode will be reverse biased, and diode will immediately switch off, and current will flow through the load and returns through D1. It will return to D1. So, that is these portions. During this period, T2 and T1 are conducting. Now again at this point, T2 is off, T2 off. So, T2 off, what will happen? Immediately the current is unidirectional in the load DC value, it will freewheel through the diode. So, this way we can have a unity power factor. So, always here the quality of the power supply is very good as far as the power factor is concerned. We have taken fundamentally at 0 displacement with respect to the phase angle between the voltage and the fundamental current is 0 here. So, what will be the type of voltage waveform appearing across the load? If you see during the conduction period, that part of the waveform will come across the load. If you see here, this is the conduction period here. During this portion, the voltage waveform, that part of the voltage waveform will appear across that is this much portion will appear across the load. Part of the sine wave centered at the peak point of the sine wave. That we are assuming the input main C in sine wave. It will appear across the load. Then during the negative portion, it will be this portion, but it is rectified waveform, so it will come this way. This will come across the. This is due to this. This happens from due to the force commutation using the thyristor. Here, what will be the output DC voltage with respect to firing angle? We know this is 0. This center will be pi. So, the output ripple frequency is 2 times the fundamental. So, what will be the output voltage waveform here? The period is equal to pi, 1 by average value. So, 1 by pi average value integral, let us take Em. We can take Em sin omega t or cos omega t, Em sin omega t d omega t. Em sin omega t means the lower limit will be alpha, that is the firing angle. What is the upper limit? This is pi by 2. Upper limit will be, see this is symmetrical. So, this is if this is alpha, this distance is pi by 2 minus alpha. So, here it will be pi by 2 minus alpha. This you can integrate and you can find out the output DC ripple for this one. Okay. Now, we have 2 degrees of freedom. One, previously all the phase angle control we had only 1 degree of freedom. 1 degree of freedom, and we can only have the start of the firing angle, that is alpha, start of the turning on the devices. Okay. Now, here, but switch off happens whenever the other thyristor is symmetrically fired, or during the negative portion of the voltage waveform, again same alpha starting from the 0 crossing, we have to fire the next thyristor. Now, here we are not that type of commutation is called natural commutation, but here we are doing forced commutation, but we require one extra diode here, but power factor improvement is there. In this case, during this 2 degrees of freedom, what extra power factor improvement is there? What are the additional advantages possible? Let us take one case. Let us take in one case, I will again draw the waveform, thyristor, diode, thyristor, sorry, I will remove this one. Diode, our load is again T1, T2, D1, D2. Let us do the input mains here. See, we are in a sequentially we are coming to one point here. Previously with the firing angle, the displacement keep on increases with respect to the firing angle. Now, with the semi converter, we made that displacement were reduced to alpha by 2, that phi. Now, with the force commutation we made that phi is equal to 0. Now, is it possible for us to make phi negative, or the current is leading with respect to the input current is leading with respect to the mains? Let us see a waveform like this. We are always firing at alpha is equal to 0. Let us say the firing is with respect to this one, and we are turning off here. This is the turning off portion, the force commutation, T1 off. So, what will happen? This is the portion of the voltage input voltage waveform coming across the load during the positive half cycle. The negative half cycle, again we are turning on at this point. So, at this point we are T1 is on, T1 on, we are giving the gate pulse. Here we are turning on, at this point we are turning on T2 on. Again at the same distance we are with respect same as here, we are turning off T2. T2 is off. So, what will be the type of current waveform you will observe here? Let us so if you take here the current waveform, at this point freewheeling starts where beta is there, this point. So, current waveform will be here, comes here, till this side it will be 0, then again it goes negative here. See, this way it goes. So, if you see here the fundamental, if this is the fundamental voltage, the fundamental current is leading the mains voltage. So, by this type of application where leading current, we can use it in compensation for line voltage drops. Suppose in line voltage drop, large inductance is there is a L omega drop is there. So, by giving a leading current, so that drop can be that line drop can be, we can compensate here. So, these type of things are this one way of this is the another advantage of this 2 degrees of freedom. Here the fundamental supply current leads the voltage. So, the displacement factor is leading, and as I told, this feature may be desirable to compensate for line voltage drops. So, okay, power system line drops, we can use it, line drops, we can use this one. So, what I want to bring here is, so here we have 2 degrees of freedom, that is, we can, whenever we want, we can turn on the device, whenever we can turn off the device. So, what is what we achieved from here? By doing this way, what we want it is, we want unity power factor. The fundamental voltage and the fundamental current should be in phase. The displacement should be 0. So, we are always talking about the fundamental current. So, fundamental current, if you see here, if this is our mains waveform, and we told this current is symmetrically placed here, the input mains current, the input current drawn from the mains. So, fundamental is in phase with the input voltage. That's a one advantage. This is the fundamental. This is the fundamental current. But if you see here, this waveform, if you do the Fourier series, it has the other harmonics. Okay, fundamental will be there, that is the desirable one. Then we have the third harmonics. If you do the Fourier series, 5th will be there, 7th will be there, 11th will, all these harmonics will be, currents will be there. These harmonics, these harmonic currents, the third harmonics will be something like this. This is the third harmonic component. Similarly, 5th harmonics will be there. This is the third harmonic. So, these currents anyway will be there. So, fundamental third, if you take a large number of harmonics and when we sum it, you will get the fundamental, the total input line current, that is this one, you will get it. So, the fundamental only will be giving the power, that is, if you say assuming the efficiency is 100%, the input power here Vrms, that is, in this case it is V fundamental RMS, then I fundamental RMS will be equal to our V0 into ID. ID is the total DC current. But still there are the harmonics are there. These harmonics, what it can create? It can also create heating losses, I square R losses, because the power circuit, also the device drops. So, it will also consume some power, but it's not useful power, that is not available at the output. This get wasted there in the device. One is I square R loss, I square R heating loss. So, efficiency of the system will come down. Now, one way the efficiency or the quality of the power supply system we improved by force commutation, making the power factor unity. Now, there are harmonics. So, how to suppress these harmonics? One way to suppress these harmonic currents, can we use some filter, some sort of filter, so that the fundamental will pass through and the harmonics will get, harmonic current will be suppressed. Okay, this we can, this may be possible theoretically, but whenever we give any proposition, that is variable control voltage, for practical application, we should give a cost effective solution also. So, here without harmonic filters, is there any way we can suppress the harmonics? See, let us come to this one, let us study about how we can do it. Here we have to use pulse width modulation. Okay. Here we have to use pulse width modulation. This idea taken from the communication people, pulse width. Their advantage of the pulse width is we will shift the high amplitude harmonics Here the high amplitude harmonic, after the fundamental high amplitude harmonic is the third one. So, we want to shift the high amplitude harmonic to the high frequency side. Suppose the high amplitude harmonics we can shift it to 11 times the fundamental or 13 times or 20 times the fundamental or 21 times the fundamental. What will happen? If you do that way, whether is there any advantages here? Let us study about that one, how we can use it. See here, not how to control the harmonics at the high side, not the current harmonics, we have the voltage harmonics. See, whenever the current harmonics is there, there should be a voltage also there. So, voltage harmonics we should shift to the high frequency side. See here, if you see the voltages, this is the voltage we got. Okay. Now, this voltage also will have the fundamental output side, fundamental as well as the harmonics. Okay. So, these harmonics, so far we are talking about only the DC value, but if you see the voltage waveform across the load, you have this type of ripple waveform coming. So, what we want, the ripple voltage will have the ripple harmonics also, that is ripple harmonics, what are the thing, fundamental, no, apart from the DC value, other harmonics. Here it will be 2 times the fundamental, then its other multiple will be there. So, this harmonic voltage will generate its own harmonic currents. So, these harmonic currents at the load side, we can create losses. So, what I want to tell you now, this how to suppress the harmonic currents or harmonic voltages at the low side, so that the harmonic current drawn by the harmonic current drawn by the harmonic ripple we can be reduced, because as the high frequency increases, L omega increases. So, the current due to the harmonic current will be decreased. So, here I told we have to use the pulse width modulation. So, let us see how we can do it. So, let us talk about pulse width modulation. What is the basic idea behind the pulse width modulation? Let us take a square wave. This is a square wave, this equal width. Let us take a square wave current. Let us take this current is flowing through a resistor. Okay. So, ID is the peak value, this is the R. What is the heat generated, the power, the energy dissipated in the resistance? The power is equal to ID square, this is ID square R. This much watt will be dissipated, multiplied by the time, give the total energy. Now, this current pulse, square wave pulse, again value of ID, I will be chopping like this. So, here this is also ID minus ID. Here also the same pulsed current, if we pass through the resistance, here also power dissipated will be equal to ID square R, ID square R, and multiplied by T, that is the energy. So, equal timing, equal energy will be dissipated in the resistance, whether this current shape is square pulse or the narrow pulse of high frequency. So, what is the difference between these two? As far as the power is concerned, these two current waveform, okay, or if this is the voltage waveform, if the voltage appearing across the resistance, then the power dissipated will be V square by R. So, in both cases the power dissipated, whether if you take the current point or voltage point, this current the power dissipated will be the same, or the energy for a particular duration is energy dissipated in the resistance will be the same. But if you see here, assuming if this is a voltage waveform, if this is a voltage waveform, as far as the energy is concerned, this voltage waveform, this will have the same energy content from the resistance point of view. But how about the harmonics? If you do the Fourier series, this will have a frequency. If this is the period T, if this period is the T, it will have the fundamental frequency F1 is equal to 1 by T, and next harmonics will happens 3F1, 5F1, that way it goes for this one. Now, how about for this one? This one, the fundamental frequency will be, let us see, this is small t. So, the period is much less. So, the frequency F1 for this one is equal to 1 by T1 is much higher than this one. This F1 is much higher than F1. So, the harmonics, the multiple of this one, 3F1, 5F1, 7F1, all these harmonics will be much greater than this one, that is 3F1 will be much greater than 3F1, 5F1 will be much greater than 5F1. So, what will happen? If such a voltage waveform, so as far as energy is concerned, so what happened is the energy of the system at various harmonics here is shifted to a higher frequency here, the second wave, but the total energy it dissipated when it passed through if it apply across the resistance, the total energy is the same. Okay. If the voltage is, it is V square by R. But in the second waveform, the energy is shifted to the high frequency side. So, suppose let us take a waveform where this type of frequencies, the chopping is done in such a way that if we can done the fundamental main waveform, if we can chop it into high frequency side, then what will happen? The current, the ripple voltage will be coming across the load at high frequency side, at high frequency, and the current drawn by current will be what is that? If the amplitude of frequency F1, if it is V phi, the impedance, if the load impedance is equal to L phi into 2 pi F1, that is L omega. This is L omega for the second case. So, this impedance will be much higher than L omega F1 will be much higher than L omega F1 due to F1. So, the F1 is subscript omega F1. So, the current, if for the voltage same frequency component, the current drawn by the load will be much amplitude will be much lower than the case where the square waveform is applied across the load. So, what is the advantage? The harmonic currents can be suppressed, but the total voltage depends on the total area divided by the by the period. So, instead of concentrating all the area in one side, we can distribute, we can chop it. If you do that way, the output voltage, the harmonic spectrum, the harmonic losses of the system can be reduced. Here we use PWM operation. Let us take how we can do it. Let us take our mains waveform. Okay, this is the negative side. Negative side we will put it here. Okay, rectified mains waveform. This waveform we will be comparing with a triangle wave. High frequency triangle wave. High frequency triangle wave we are doing like this. This frequency of the triangle waveform is high compared to the our mains. Then see, if you see here, let us take the our single phase converter here. T1, T2, D1, D2. Previously we said we can turn on T1 at any time and we can turn off T1 thyristor 1 due to force commutation any time. So, let us take the case when this our mains is greater than the triangle waveform. We are turning on T1. That means our sine wave V sine greater than triangle. We are turning on T1, T1 on. When V sine less than triangle will be T1 will be off. This is during the positive half cycle. Positive cycle. Now, our turn on turn off of T1 is independent of turn on turn off of T2. Now, during the negative half cycle, again when V sine greater than triangle, T2 on, V sine less than triangle, T2 off. Then let us see what is the type of voltage ripple coming across the load. So, here first condition, sine greater than the triangle, that is this point, up to this point sine is greater than. So, during this portion this much part is coming across the load. So, again for clarity I will draw the repeat the sine waveform here. Negative we have rectified it. So, rectification happens at the converter side. So, during this portion whenever sign is greater than top switch is on, this much portion will be appearing across the load. Okay. Then again here, at this point you are turning off T1 on, this is off, that is T1. Again during this portion it appears across the load, that is here. Again here till this point, again here. So, here waveform triangle is not drawn properly, otherwise you will get symmetrically placed pulses here. The same thing happens here also, in the other side also, sign greater than the. So, here we will be turning on and T2 will be turning on and T2 will be turned off at this point. So, this type of pulsed waveform coming across the output load. Previously, part of the full part of the mains waveform was coming here. Here is a pulsed part. Now, the average value depends on the area, total area divided by the period. Here period is 1 by pi. So, as I told before, this pulse waveform we can have the same output DC voltage, but what is the advantage here? Because of the pulse frequency, the input current waveform, how it will look. Input current, whenever T1 is on, you have the input current like this. T2 is on, we have the current like this. Sorry, T1 is on, it will be like this. That is rectangular pulses. In the negative side, you have like this. Fundamental will be here also we have unity power factor. But what is the advantage? Because of the pulsed waveform, these pulsed waveform have high frequency component. So, the harmonic currents drawn by the load will be much less compared to the previous schemes. So, this way the efficiency of the system can be improved. At the same time, output voltage can also be controlled. Here, how do you control the output voltage? So, we found the pulse width duration. This duration depends on the period during which the sine is greater than the triangle. As the sine angle decreases, so let us take a case like this. The pulse duration, the T1 will be on for very small durations in the one period here. So, similarly output voltage will, output DC will also vary. So, triangle frequency is fixed, sine amplitude we will increase and decrease such that the output voltage is controlled. At the same time, the ripple frequency, output ripple frequency are shifted to the high frequency PWM side. This how the PWM in the sine triangle PWM, how the frequency components are shifted, will come to that one later stage. But here we can we have to know that the next higher order harmonic, not the fifth times it will go to the, not with respect to the fundamental, it will go to the with respect to the triangle frequency. So, if you use higher triangular frequency, the current, the harmonic currents drawn by the load can be reduced. But the problem is with the thyristors. Thyristor requires a fine, we have require external turn off circuits. So, high frequency PWM may not be possible with the thyristors, but presently available IGBTs, we can have high frequency PWM. So, how we can have a output voltage control with the unity power factor, okay, for positive for the output voltage directions using PWM we will be studying in the next class. This is present day available IGBT makes it convenient to have variable voltage control with unity power factor, high frequency PWM using that is front end AC to DC converter with PWM converter with unity power factor. So, a lot of converters are available, one converter we will study. Originally I think this converter was used for traction drive applications for front end converter, AC to DC converter, where the input was single phase. Then how the harmonic suppression we can do with the sine triangle comparison, we will study in the next class.